So the coffee bot can be controlled from any browser by getting the user to open the IP address of the robot on their network, and that loads using HTTP this website, which contains the HTML for this page and the JavaScript for the code behind the buttons. And when the user presses a button, for example here, when I press forwards, the robot will move forwards, and stop, the robot will stop. What's happening behind the scenes is that each of these buttons is submitting a post request through to the web server to instruct the server on the desired rate of movement forwards and rotation of the robot to the left in meters per second and radians per second. These are then converted into a command and topic that is published through to a HiveMQ broker running in the cloud. And this runs in the cloud and then enables any clients listening to this particular topic to receive the message. In this case, there is another client running on the robot itself, which is listening to the same message that it receives, checks that it's an appropriate movement command and it's for its device rather than for the other devices, which could be anywhere in the world, and then converts that into a message to send through from the Raspberry Pi into the Mega using this USB cable that connects the serial ports. And when a command is received on the serial port, which is checked in the main loop, this is then converted into using an algorithm called brake steering to work out the desired rate of movement for each of the wheels. Because since we know the diameters of the wheels and we know that the maximum rate that they can turn at according to the spec is 125 revolutions per minute, we can calculate based on the rate that we want the robot to move how much to turn each of the wheels to achieve the desired movement forwards and rotation. For example, to move straight forwards, we'll turn all the wheels at the same speed, so the robot moves forward. And to move it backwards, we turn them all at the same speed backwards. To produce turning at the same time as moving forwards, if we want to turn to the left, then we'll leave the left wheels off and we'll turn the wheels at the right fast. And that will push the robot around to face the left. If we want to move backwards, but also turn to the left, then we can leave the wheels to the right off and turn the wheels to the left backwards, which will pull the robot back so that it's moving backwards, but also turning to face the left. And in this way, we can achieve, within the limits of what the motors can provide, movement and rotation within this 2D plane. Now these are only estimates, and we are integrating additional sensors such as wheel encoders that can actually measure the velocity that the wheels are turning at to ensure that it is the same as our theoretical expected rotation, and IMU to sense the rate of movement based on acceleration and changes in the gyroscope to detect rotation, and also connect with computer vision to detect locations, relative locations of certain features within the picture that it sees and how they change from one frame to the next to enable it to work out how far it must have moved along the ground. But this basic movement, just using this dead reckoning algorithm and brake steering, is enough to get the robot moving to some degree based on user control.